Hi everyone, today we're going to start Unit 9 with Topic 9.1, Introduction to Entropy. So entropy is a measurement of randomness, otherwise known as disorder, in a system. Its units are in joules per mole times Kelvin, and positive entropy increases disorder, negative entropy, or negative values of entropy, decrease disorder. In other words, it is more ordered. So for example, if you have a glass of just ice cubes that has really low entropy because it's ordered, right? It's in a crystalline structure. As you increase the entropy, you melt the water. You melt the ice into water. And so the melted ice, those liquid water molecules, move around a lot more. Because they move around a lot more, there's a lot more randomness. It's more disordered, so your entropy goes up. Same thing here, right? This is a metal or a salt. As you heat it up, you gain more entropy. It becomes more disordered. And the symbol that we use for entropy is S. And oftentimes we'll see delta S, not similar to delta H. Another way to think of entropy or randomness is to think of what are known as microstates. Microstates are just the total number of possible configurations of a system. And so if you have more ways to configure a system of molecules, you have more disorder and it is more random and your entropy increases. So there's a few factors that increase entropy. One is temperature. Volume will change your entropy. The number of independently moving molecules, gases, which form from solids or liquids, so essentially a phase change, but specifically to a gas. Liquids or solutions form from a solid. In other words, you melt it or dissolve a solid. That will increase your entropy. Or the number of gas molecules increases in a reaction. So all of these things will increase the number of microstates. In other words, your entropy or your disorder will go up. And so in the next few slides, I'm going to explain all of these a little bit just to get a better sense of why entropy is going up. So first, let's look at volume and temperature. Take the case of volume. If volume increases, this means there's more room for molecules to move. This means more microstates, right? You have more possible places your molecules can be, so entropy goes up. For temperature, right, more temperature or a higher temperature equals higher kinetic energy. If you have more kinetic energy, that means that your molecules have a greater distribution of speeds, and so there are more microstates. there's more microstates, what that essentially means is entropy goes up, or in other words, S will go up. So if you increase volume, your entropy goes up. If you increase temperature, your entropy goes up. Phase changes will also increase your entropy. And so entropy of a system will increase if gases form from either solids or liquids. And so if we have a reaction of, say, a solid plus a solid makes a gas, or a liquid plus a liquid makes a gas, or even a solid goes to gas, right? Anywhere, any reaction where you're essentially making a gas from something that isn't a gas, entropy will go up. Liquids or solutions form from solids, and so if you have S plus water, right, something solid dissolving in water to make an aqueous solution, that'll increase entropy. Or the number of gas molecules increases during a chemical reaction. In simplest terms, when you look at a reaction, the side with more moles of gas will have the higher entropy. So if I have, for example, right, H2O liquid going to H2O gas, if I have 1 mole of this and I make 1 mole of that, this has a higher entropy. And this is exactly what I was showing on that last slide there, right? Ice, you have very little vibrations, very little movement. Liquid water, they're free to vibrate, they're free to rotate a little bit, and so they have more entropy. Where if it's a water vapor and it's a gas, they can move around, directionally because they're not bumping into each other. They can rotate, they can vibrate. They have as many different microstates as possible because they can move as much as they want. Now, all that brings me to the third law of thermodynamics. We already talked about the first law, and we won't really talk too much about the second law of thermodynamics. But the third one says that entropy of a pure crystalline substance, in other words, a solid, at absolute zero being at 0 Kelvin, is 0. And so when you're at 0 Kelvin and there's no molecular movement, your entropy is at 0, which makes sense because they can't move around. If they can't move around, there can only be one microstate. Essentially, at 0 Kelvin, absolute 0, your entropy is 0. And you can see this graph here. In a solid, it'll slowly increase as you increase the temperature. Then there's a big jump when you do your phase change. That's the melting. Then you have slow increase for a liquid. Then again, a really big jump as you increase the temperature. And then when you're in gas form, you will also have a slow increase of the entropy. If you remember this kind of looks like a phase change diagram, just kind of flipped on an axis. And now here's just a big summary if you want to take down these notes for yourself or refer to it when you're doing practice problems. On our left here, we have entropy increases. On our right, we have entropy decreases. So decomposition reactions, increasing temperature, solvation, dissolving something, a phase change that's endothermic, solid, liquid to gas, a reaction that increases the number of moles of gas, or gas expansion, P goes down and V goes up. All of those will increase your entropy. And the exact opposite is true for entropy decreases, right? A synthesis reaction decreases your entropy. Lowering your temperature, precipitating something, an exothermic phase change, so going from a gas to a liquid to a solid, decreasing the number of moles of gas, or compressing something, decreasing the volume and increasing pressure. All of those will decrease your entropy. So let's look at this one practice problem here. We can see this diagram. We have NO2 on our left, and that makes N2O4 on our right. Essentially, this is a synthesis reaction, right? We have 2 NO2 react to form 1 N2O4, both of them being in the gas phase. And so we know since this is a synthesis reaction, our entropy should be going down, right? And so from there, we can immediately say C and D can't be possible because we know entropy is going down. If we look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles or 10 molecules of NO2. And here we have 1, 2, 3, 4, 5, 6 molecules, well, 4 molecules of NO2, 4 molecules of N2O4 and 2 of NO2, right? And so here we have 10 molecules of gas, and on our right, we have 6 total molecules of gas. So on our right, we have less molecules of gas. If we look at our two options here, it says delta S, or the entropy is going to be negative. because the number of N2O4 molecules increases as the reaction proceeds. That really doesn't cause anything here. It doesn't matter if N2O4 is increasing. What matters more is that we have less molecules of gas on the right versus molecules of gas on the left. And that's exactly what B says. It says the number of molecules in the gas phase decreases as the reaction proceeds. And you can see that's exactly true. And so here, our answer would be B. We decrease the number of molecules in the gas phase, therefore we will decrease the entropy, or we decrease the value of delta S, not of the whole reaction. We'll go over some more practice in class, but for now that's all. Thanks, guys.